All right, so we just found out how to do tabular integration. I said anything that you can do with integration by parts, you can do with tabular. Anything you can do with tabular, you can do with integration by parts, because it's just tabular integration is just a repackaging of integration by parts. But then you might ask, okay, so is it always better? Well, there must be some downsides. There must be pros and cons somehow, or else everyone would be always using tabular, not integration by parts. And I have to say there is sometimes a downside to using tabular integration. And it's the case when you can't put the polynomial on the derivative side. So we did this example earlier today, right? And according to Liate, it says we should be integrating which one? X cubed should be the one that's integrated. Ln of x should be differentiated, right? So when you try to apply the tabular here, plus minus d and integral, you should be placing x cubed here, and ln x gets placed here. Which means you don't have a polynomial in the d side. And the downside of tabular integration is that if this is not a polynomial, then it's not going to hit 0. And that means you have to know when to stop. Now, I still prefer tabular because it's a lot simpler and faster for me. So I'd rather choose to memorize when to stop. And it's not that bad. Okay? So you only need to remember two cases. One is when you have logs. Okay? The other case is when you have, one is when you have logs or inverse trigs. In that case, you just do it once and you stop. Okay? The other case is when you have exponential times trig function. In that case, you stop when the same thing appears again. So you stop at the third line. You just remember this, and you can always use tabular without any problem. Okay? So let me show how that one works. So as I said, you stop in the second row. Now, why do I say this never stops? Let's actually try to see what happens if you try to continue to differentiate. Ln of x differentiates to 1 over x. 1 over x. 1 over x differentiates to negative 1 over x squared. This differentiates to 2 over x cubed. Differentiates to negative 6 over x to the fourth. It just becomes more complicated, and it never stops, and you don't want to do that. All right, so that's why you need to know when to stop, or else it's going to go forever. And we just know by working on the integration by parts side that this is the place to stop. All right, so I mean, there's a reason why I still taught you how to do the integration by parts, even if tabular integration can do it all, and much faster, much efficiently, because you need to have that understanding to really appreciate this and also know the inner workings of this. Okay. So this integrates to 1/4 of x to the fourth, and there's an alternating plus minus. You should always start from plus, and you should alternate. And this really keeps track of that annoying minus sign in the tabular in the integration by parts. There's a minus sign in the integration by parts that keeps switching signs, right? That's what this is doing. Right? So we have everything built up. And this time there's only one missile, because if you do this, then there's 1/4 x to the fourth ln of x. But then if you do this, there's nothing to fold down to. So this doesn't create anything. So there's only one missile. Okay. What do you do afterwards? There's one rifle shot, right? Yeah, one rifle shot this way. Okay. Let's see what that is. X to the fourth divided by x is x cubed. 1/4 and minus, it's negative 1/4. And what's different this time? This last line has to be integrated. Okay. So that last line has to be integrated. And that's not hard to integrate. Negative 1/4, you can pull it outside. X cubed integrates as x to the 4th. You add 1, put the reciprocal in front. So that this is negative 1/16 x to the 4th plus c. So when you only have polynomials here, then this last line really doesn't do anything other than to create the plus c. But in these other cases, they do play an important role, and you should never forget to use them. Okay? That's why I've seen some textbooks where they don't talk about this at all and only allow tabular for the case when you have polynomial on the d side. But I really like this method much more, so just try applying this for every integral parts question. Okay? So what's the final answer? This plus this, right? So the answer is 1/4 x to the 4th ln of x minus 1/16 x to the 4th plus c. And if you check with the earlier answer, you'll see that they're exactly the same. Now, next time we're going to try the exponential times trigs and get the same answer as well.